Thank you, Standa, and thank you to the organizers for inviting me to here to give a presentation. Yeah, I know it's usually your lunchtime already, right, Standa? Now, so I'm sorry that there is one more lecture, and I will try to make it somehow interesting to you. Even so, it is like now about one more, a different matter. It's now with fluids involving. But it sort of relates also to the lectures, to the other lectures, because we have like this elastic solid, which is sort of related maybe to the last lecture. And of course, for the elasticity, you also need to understand the Jacobian a lot and have to take care about invertibility. And actually, we at some point, I think we also use the CLA Netsch's condition. Yeah, so there's a connection. So this is actually about several works up to now. And it was achieved in collaboration with Barbara Benesova, who is here, Dominic Breit, who is now in Clausthal, I think currently maybe, and Malte Kampschulte, also from Prague. So here are the possible regimes, at least that I'm aware of fluid structure interaction. And maybe to sort of have a warm up here, we focus on the easiest one, which is this rigid body motion here. So you see this red object, which is floating in the fluid. So the blue stuff is the fluid here. So let's have a look. This is the canister. Here's some water inside. And then maybe we kick the ball inside and there's no gravity for some reason, or maybe if there is, then it would sort of fall down here. But this it would do in such a way that it's in interaction with the fluid, so the fluid would put certain friction on it. And this, and moreover, also, of course, reversively, like the motion of the solid would also move the water. So the water would have to move in the reverse direction. So essentially, the coupling is always over the interface. And the first one is something like a boundary value, which is that the speeds are equal. So the fluid velocity would be equal to the time derivative of the motion. So the eta is always like the motion of the solid. Here it is just one vector, which gives the position of the center in the rigid case. And this would be like on the boundary of the object. Or if you want to call it B as a ball, you cannot see it in the back, right? It's a K, yeah? And on the boundary of it, we have like the equality of speeds. And so this is like the first part, and this is something like a boundary value talking in PDE. And the second one is that the stresses are in equilibrium. This means the fluid stresses are equal to the, in this case, there are no stresses because it's a rigid body. So in this case, like the fluid forces at the boundary summed up. So can put here some Hausdorff measure if you want. So of the fluid forces at the boundary, they would then equal to the momentum of the solid. So this would create momentum, and this is how essentially this would friction down. And if you also have gravity, you should also put it somewhere here as a forces. This would be minus G, right? Something like that. And this would be the PDE, and this would describe the motion. And so this looks nice and simple, okay, more or less. And this also means that because of like this fixed geometry, so still the domain of the fluid would change in time, because you would consider the fluid also always in Eulerian coordinates. So you would always take the current domain and look at the fluid velocity at every point in time and space, and also at the pressure value at every point in time and space. This is what you use to describe a fluid. You don't have a deformation for the fluid. For the solid, you will have a deformation. But they're very different matters. And this is characterized by these different regimes and these different domains of definition, the different quantities. Yeah, but still here in this setting, the geometry of the fluid is rather simple, and you can sort of use a straightforward change of variables and use a steady existence theory for the fluid, and this is already known for some times. And since this lecture is all about constructing of solutions, so about existence, this part is sort of the easiest reference. What is a very important and very well-studied regime is the regime of plates and shells. So in this case, you would have a fluid again, and on top you would have an elastic plate, which can deform if somehow you put some fluid, you let something flow in or something, then it would go up, and then maybe it would start oscillating, but again in a damped way. And here, if you reduce the setting and use like some linearized Coiter shells, for instance, or you just fix the direction which you deform the plate, then you can actually use fixed point methods, some small deformation regime essentially, it stays. And yeah, you can also use different approaches here to construct solutions. And moreover, in this regime, you can even use the fluid very good to help getting regularity for the shell, getting regularity for the hyperbolic PDE, or if you take a perfectly elastic solid, you can actually show even no existence of nonlinear hyperbolic equations in this regime, because you have the fluid, which makes it a dissipative system. And in the existence theory, if you have a hyperbolic PDE and you don't have any viscosity, so if it's perfectly elastic, it's a difficult setting. If it's nonlinear, then you have like beautiful examples which show you that anything can happen in general. But the fluid helps here. This is sort of the message. And let's say the case which was really more or less completely open when we started working on this, so Barbara, we started on this like a few years ago, was like the large deformation case where you have an elastic bulk inside a fluid. And actually for this setting, already to include inertia was somehow not known, I think. And we managed to do this on the way. So it is also, the results are also relevant for elastic deformations alone. Okay, so this is the horrible literature reference slide. It's just sort of to demonstrate that there are many results and very classical, very important results in all these regimes. And somehow what I wish to point out here is that if you look about for the weak solutions, then this last contribution here, is there something like, I cannot use the pointer, this is red and I have this color blindness, so I never see this, but this is robust. So this last result here, which was also produced in Prague with Gianmarco Sperone, is now in Milano, actually took also the large deformation case to the elastic plates case. So there we have large deformations. This means including tangential motions, and it's built on the methods which I'm going to show you today. And so for the elastic bulk solids, there are some very classical and very important results for short time existence, linearizations, or even fixed geometries where you just have like a interior shearing acting on the fluid. But we considered like the large deformation case. This is like this paper, and we also moved it to included compressible fluids here, and I will talk about these two results today. Okay, so here's the setting again. Now we have this largely deformed solid, and so this creates like the mess with the fluid. So for the solid, first everything is maybe as always. So I focus here on the three-dimensional case. So the picture is two-dimensional, of course. So we have a deformation map which is unsteady, so it depends on the time variable, and it goes from the reference configuration Q into the Eulerian domain omega. and it's a subset of this. And wherever there is no solid, there will be the fluid. And the fluid is, as I said already, prescribed by a velocity, which is a vector, and the pressure, which is scalar, sort of saying where it wants to move. And then we have for the solid an elastic energy and a dissipation potential. So let's be, I think here we are, like this is the most important slide. So take your last concentration, please. So this is like the solid PDE. Yeah, we have like here this stress tensor from the solid, which is given by some Fréchet derivatives or Gateau derivatives of the dissipation potential and the elastic potential. And sort of the trouble is that because we have large deformations, we need to make sure that our energy explodes if the determinant, the Jacobian, goes to 0. So here's the Jacobian. And if the Jacobian goes to 0, then this term explodes. And this is necessary if you consider large deformations, because otherwise you can squeeze things together for free, I mean, for finite energy. Yeah? And this is against the physical assumptions. Okay, moreover, it should be invariant under rotations. That's why you use this deformation gradient here. Yeah, you penalize how far away you go from your reference configuration, which is the identity in this example here. And you also put some regularization term in order to match to, let's say, the theory where you can write down an Euler-Lagrange equation, which is necessary because we want to couple fluids and solids. So we have this huge regularizer here, and we have, let's say, the simplest possible energy which does penalize the compression, but still we already have horrible problems. And with horrible problems, I mean horrible problems to use existence theory which was available at this point. And this is due to the fact that actually here you need to minimize over a non-convex space. You need to exclude negative determinants. Yeah? And non-convex sets are topologically problematic. Yeah? And so these fixed point theories which were used, or other construction methods where you at some point use something like a fixed point method, are not admissible. Yeah? You cannot do it. Non-convex set, why should you have a fixed point? Yeah? And that's why you have to find a variational approach here, because you can still minimize. You can always minimize. Yeah? And yeah, that's why we need a variational approach here. And yeah, this is exactly the main message. So yeah, lecture is the key message is already set here. Yeah. Okay. Here is some dissipation potential. Also here you should make sure that it's somehow independent of the point of the observer. So yeah, this is a classic example. Actually, in the lecture here, I will use the Laplacian of dt eta, or the gradient of dt eta, to simplify notation, but this is sort of the physical one, which we also used in the papers referred to. Okay, so back to fluid structure interaction. So here are the strong formulations. This is now the quasi-steady model, so we don't have inertia here. So this means no inertia for the fluid means that the prominent material time derivative is missing in the Navier-Stokes equations, and you are left with the steady Stokes equation here. But the domain always changes, yeah? So you always have to solve a different Stokes problem. Yeah, it should be incompressible here still. And here you have like some stress tensor which equals a given forcing. And the forcing we always consider in Eulerian coordinates, but you could also take Lagrangian coordinates if you want. So that's why we compose it here. So this is like, as I said, at the interface we have this equality of speeds, also known as no-slip boundary conditions. So the fluid moves with the body. and we have this coupling of the stresses at the boundary. So this maybe looks not so nice. The good thing is you can hide this in the partial integration. And so you can write down this weak formulation here. So this is the E prime actually. So this E prime, now the variation acting in some direction phi. This is now my dissipation potential. As I said, it's like the Laplacian of dt eta here, and henceforth. Here is the dissipation of the fluid coming from the Stokes. So this means the symmetric gradient here. Here's the pressure part acting on the divergence of a test functions. And here are maybe some right-hand sides, this one and that one. And now the point is, and this is a very nice trick, is that all the geometric troubles you put sort of to the test functions here. So you take an Eulerian test function and you take a change of variables such that you have the right test function also on the Lagrangian domain. So you have this global Eulerian, let's say, experiment if you wish, and you just take the respective mapping for the solid variation. And then essentially this change of variables happening here and there does produce the equality of the stresses. So it is here something like a Neumann boundary condition because it comes from the equation directly. This is good. People are still paying attention. I'm very happy. I mean, these slides look horrible. Always when I prepare lectures of this subject, I always think, oh my God, it's so big, so many equations. Okay, but here is now like the method, Barbara's trick, I would say. And the trick was, okay, here's the minimization now for the quasi-steady setting. So we are in the quasi-steady. This means, like, philosophically speaking, we are in a parabolic setting. So a gradient flow could do the job here. And so we wanted to use the George's minimizing movements here, which is variationally, which allows sort of incrementally to produce the next time step. And this worked once we sort of, once Barbara came with the right idea, which was to sort of fix the state space, take the right scaling. So this is like here, this is the viscosity of the fluid, this is the viscosity of the solid. And now we look for the next step. So this is the geometry which is already given, the eta k minus 1. This determines our fluid domain here. And now we look for the next state of the solid, and we pay a price of the viscosity here with the right scaling. And this is like this tau is very important. And this tau also reflects to this, because the W is a velocity, the beta is a state. So the W has a different tau scaling as the state. And so if you're now very careful with these dimensions, if you wish, then you minimize over all possible future states, paying with a fluid viscosity according to your new state. And so you can actually make this viscosity now smaller because you change your domain. So you pay less viscosity here. And you need to make sure that the boundary values are correct. So you minimize over all possible new states with a velocity that satisfies the right boundary conditions. And this does the job. If you do this, then you realize that if you calculate the Euler-Lagrange equation, it's an approximation of your coupled equation. And so the first thing is first maybe to show that you have uniform bounds. So this is like the, let's say, the usual simple trick. So if you have now the minimizer, you can take just the last state as a competitor, which means you take here, you don't have to move at all because you can take the zero fluid, right? Zero velocity. So if you don't move, then you have a zero boundary value for the fluid. So you also don't pay with viscosity. For this, it's clear, right? No friction then. And this gives you an a priori estimate. Typical one which you can get when you have a gradient flow and you use minimizing movements. You need maybe to use some Korn inequality for the symmetric gradient. But what is sort of like more important here is that if you take now the variation in your Eulerian direction psi, then this relates to a phi in the following way. So because of this difference quotient, so you have to make, this has to be a competitor, so it has to be a class of the minimization, right? So you take your velocity and you add this perturbation here on the same domain, and this means you also add the perturbation on the solid part. And if you take this competitor and calculate the Euler-Lagrange equation, you get the approximation of the weak formulation which we wanted to prove the existence for. Okay, so this was like, this is the most fluid part here now. And now, yeah, so maybe this already was like the first like large deformation fluid structure interaction result, but it's all in one paper. So now we wanted to include inertia. And we realized, okay, maybe also for the solid alone, this is a bit of a problem. So let's look at the solid. We have now the inertia here. This is like the simplified viscosity. And we have an elastic energy, which has these negative powers of the determinant. So, Sander, until when can I talk, by the way? I take lots of time. But when is it over? 20 minutes. Okay, good. So, inertia. And now, for this, we introduce these hyperbolic minimizing movements, but I want to make very clear, of course, this is not a hyperbolic PDE, right, which we're solving. But we are suggesting a scheme which is able to produce approximations for hyperbolic schemes, hyperbolic PDEs. Okay, so here's the parabolic de Giorgi's minimizing movements. You look at the next state, you pay a price of dissipation for it, but you get maybe a better energy. So they are in competition. You pay because you move, but you get a smaller energy, and this is the beautiful gradient flow, which eventually converges to the elliptic solution. Okay. And this is then the perfect Euler-Lagrange equation, which is the parabolic PDE. Now, the hyperbolic one is very much similar. You just essentially parabolize your problem. So you say, okay, this is my parabolic term, and now I take a very large h, which eventually will also go to 0. But here it is still huge, and I take a difference quotient from some very far time away, which eventually will get very close. But we introduce like these two scales. So we have this tau, which is much, much, much smaller than the h. And with this formulation, we have actually a well-posed minimization problem, which is a gradient flow. We can minimize it, and we get the right approximation. That was the trick. And this allowed to produce like this approximation for the second order in time PDEs, including these horrible energies which are so physical. So this is the aim. This was the aim here. What is sort of critical here is that here now, if you take like the naive test function, you don't get anymore a good a priori estimate. You get an a priori estimate which depends on h, which is natural because the Giorgi's minimizing movements are gradient flows. So they will not give hyperbolic estimates. But because the Euler-Lagrange equation has the right structure and is really a fully implicit Euler approximation here, you can get a priori estimates afterwards. After passing with tau to 0, essentially. So you get first a priori estimates independence of h, then you can pass with tau to 0, and then you can do a priori estimates which are good ones. But they don't come from the minimization. So this is a real difference. And we want to see this difference because it's a different PDE. It's not a gradient flow. But we approximate it by 1. Okay, so this was this part. Now, the last step sort of was to realize that actually this convective time derivative is also something like an inertia. And so we essentially introduced something like a global velocity and also some, let's say, global Lagrangian map here. So what is it like this is essentially an extension of the coordinate given by the eta in the Q, and this is a flow profile. And if you regularize and you make sure that your velocity is uniformly Lipschitz for an approximation, this flow map is always well defined. So if you move along a Lipschitz velocity, this is well defined. And this allows now to write the convective term as a time derivative of this velocity here. And this again allows to take the difference quotient of this quantity to approximate this term in our, let's say, parabolic approximation of the hyperbolic. So, and this is how it looks like then in the end. You do this change of variables, and then you get like this, what we call infinitesimal Lagrangian difference quotient. Yeah? And this has the same structure as the inertia term for the solid. And you can produce, again, a good approximation. And maybe I should have said this at the beginning. The difficulty was here to get an approximation. Yeah? Usually in PDEs, or let's say for fluids in particular, to get some approximation is not so troublesome. In fluid structure interaction, it's a big issue. And here it was the key issue, to get some sequence which eventually will converge to your solution. Yeah? So, and yeah, not like you can just use Galerkin and things like that. You have to really work with this scheme. Yeah? And now we have the scheme, even so it looks complicated and it's horrible, but this is an approximation. And now you can then pass to the limit with this scheme, which I will not say how, but there are many tricks, of course. But like the key is to get an approximation here. So here are some messages. It was somehow very important that you keep the scheme explicit with respect to the fluid domain, so you don't variate the domain because this creates a mess. And also you should be very careful with the different metas because they have different properties. So to mollify the domain is also not a good idea here. So one should keep the interface between solid and fluid very sharp here. Yeah, and somehow this is an issue. So the divergence freeness of the velocity is like a time-changing domain. So this was technically very problematic for us. Okay, and so this is funny. This is still open. Yeah, so you can get the unsteady solution, but the steady solutions, we don't know if they exist. Yeah? Maybe they don't exist in some cases. Yes? So you put the forcing on the fluid, so it is non-trivial. But in the end, it should be zero at the boundary because the solid should not move. If you don't put the forcing on the fluid, of course it's trivial. Then you just relax. That's it. Yeah, this is solved. But if you put the forcing on the fluid, so some inflow, will it move forever, the solid, or will it go to one state and stay there? I think it's an interesting problem, really, but very difficult, at least in my opinion. Okay. So I think, okay, this is the theorem, right? Yeah. Nice, yeah? So here are some conditions and to get the object. Okay, 10 more minutes, right? Or 5. Something like this. So let's make things more complicated, just for fun. And this means we make the fluid now compressible. maybe this is not too stupid because the solid was also compressible. Yeah? So we have now compressible solid, compressible fluid. This means we have a variable density here, and otherwise it's the same. The density is the new guy. And now the equations change a bit because now the momentum is actually on the, looks different. It's like the density times the velocity, so this is variable, so it changes the equation here. And moreover, the pressure looks different because you don't have the divergence-free condition. The continuity equation is now like the sort of the transport of the density. Not quite, but yeah, the conservation of mass, let's put it this way. That's the right term. And then where there is a lot of fluid, you have a lot of pressure. And where there is no fluid, you have a very low pressure. So you will want to sort of equalize your stuff. And this is like this compressible Navier-Stokes equation here. And yeah, we have the same coupling conditions. And the energy now looks like this. So you have the elastic part of the energy. You have the dissipation of the solid. You have the kinetic energy of the fluid and the solid. And you also have this, what is it called, free energy? This pressure potential here. And this, here's the viscosity of the fluid. And our theorem is that if this famous gamma here, this is this barotropic exponent, is not too small, and you have the correct outer boundary conditions and some initial data, some assumption, then we have the existence of a big solution. So what is nice here is that also this part here can be put into a variational frame. And this is really, I have to say, Malte's point. Yeah? He managed this because I thought this will be complicated. Malte said, yes, it's complicated, but possible because it's physical. So let's see. And okay, here's the approximation again. You introduce like this function h, which is this pressure potential there. And then you do this minimization just naively. So you plug in the energy what you want to have. So these are all the terms which were on the last slide now in discrete form. And here this is already now put in this double difference quotient here. Yeah? There's the h. And this is like the convective terms. So these are like the inertia terms here. The new guy is this one. You do the same minimization naively, even so you now have here the new Eulerian domain. And this was something which I lastly told you should not mess with. Yeah? And this also was my strong belief. Malte didn't listen, but it was just. Yeah? Because he said that exactly there, we can make a very nice change of variable, pulling it back to the omega k. And this works because of mass conservation here. And I think here is the slide explaining this. Yeah, so the point is, okay, it's already written here, yeah? You can now use this change of variables here and determine everything by the velocity and the state only. Because you know your last density, and you know by this formula what the new density should look like, and this is even on the old domain. Because you have this transport of the density here. And I think here's the computation. Why this now? Okay, so this is the reason why you can sort of write this minimization only in terms of the new velocity and the new deformation. So you sort of remove the new density by using the transport. So you take a new state, a new velocity, and then you look where there the density is transported to. Yeah? And then what is sort of even nicer if you do this, and this is all very physical and all correct, if you then do the variation here with respect to perturbations of this velocity, you get the right term in your Euler-Lagrange equation, which is the gradient of the pressure. And this is the computation on this slide. So if you do the variation, then you get the right term in the end. This is the divergence of the test function, and this will become the pressure potential. So the message is the scheme is physical because it's energetic. And the PDEs are derived from energetic considerations. We just take those step back, and that's how we construct the solutions. Yeah, I think I can stop here. Thank you very much.